Welcome. This is the sun, moon, and the stars. And so in this session, I'm going to give you some activities that are confirmation and structured inquiry activities. And so this video is intended to give you some more experience identifying what a confirmation and structured inquiry activity entails, and also some just really fun astronomy activities that you can do with students. Okay, so we'll start with the moon, actually. And so uh, as the teacher, you've probably used many instructional techniques to teach content relating to the moon's orbit, its appearance, and its properties. And so if we just start with thinking about the moon's orbit, the first thing that comes to mind, that things that we try to teach students, is why we see different moon phases, right? And so it's due to the moon's orbit around the Earth. And so its position in this orbit creates a different angle in which the sun, the moon, and the earth are aligned. And so the reflection of light that originates from the sun that bounces or reflects off of the moon is then visible to an observer on Earth. And so depending on the moon's position, we see that light reflecting off the moon in different ways. And so, for example, when it's directly between the sun and the earth, whenever an observer is looking up the moon, they see this back side of the moon that's not being illuminated. No light is reflecting off of this side. And so we have no moon visible, and it's called the new moon phase. But as that moon continues to orbit around, our perspective of the moon changes. And so still this same side of the moon is illuminated by the sun, except this time the observer is looking up and it sees this side of the moon closest to it. So half of it appears to be illuminated while the other half still appears to be dark. And so we call that first quarter. And so this pattern just continues as it makes its counterclockwise orbit around. And so you probably work with students on teaching them vocabulary such as waxing moon phases, the names of particular moon phases, and waning moon phases, and the names of those particular moon phases as well. And so you probably also have maybe done an activity where students then get a chance to do a craft where they make the moon phases, like the Oreo craft, where you kind of shave the filling inside into the particular moon phases as they're seen from Earth. And so that's really fun. And you probably also have had students make observations of the moon, right? And taking a look at craters and the big mare regions and the darker color regions those mare regions. And so you help students get an idea of what the moon appears like. And you probably even pose the question as to why do we only see this side of the moon, right? And so you probably have given examples of how the moon slowly rotates on its axis and while it is orbiting around the Earth. And so it's due to its synchronous rotation and revolution around the Earth that the same side of the moon, or what we call the face of the moon, or the near side of the moon, always points towards the Earth. So it's not that the moon doesn't orbit, it's just that it does so synchronously with its revolution, that the same rates will give us this appearance. And so until those rates change, we will continue to see the same side of the moon. So these visuals are in NASA Space Place, by the way. And so if you click these links in the slides, you can go to the particular pages where these animations are so that you can use them with students. So where does the confirmation inquiry come into play? Well, remember, confirmation is whenever teachers provide the investigatable question, teachers provide the method in which they're going to do the investigation, and usually the results are already known to students, right? And so in this particular activity, students are going to be provided with a moon journal, and they're going to observe how the phases of the moon change throughout the month. And so that's kind of the investigatable question, is the moon's phases throughout the month. What do they appear like? And then the procedure obviously is going out at these particular dates and times, taking a photo of the moon or looking at the moon, drawing a picture of what we see, and then recording if it's daytime or nighttime. Okay? And so by giving a chance for the students to observe all those different phases, they get to see firsthand for themselves a real-life experience of the different moon phases, and they can watch how the position of the moon changes in the sky from day to day and really feel what it is that you've been instructing to them. So that's confirmation. Structured inquiry is going to be a little bit different. And so this is all about just changing an aspect of it and adding the part that students don't already know, right? And providing them with information for them to analyze and come up with ideas about and explanations, you know, for why those things happen the way they do. And so I've constructed this moon journal that's been altered so that students can log into this or sign on to this program that's on your computer, and they can complete their moon journal. So that way they don't have to be out all hours of the night, and they don't have to worry about the weather in the sky, but they can still get reliable, accurate information with the feeling of a real world experience. And so I'm going to show you Stellarium, which is the program that this activity that I created was made for. And so notice in the data table for this that I've added elevation, right? And so in real life, students are going to be able to do this with a clinometer, which measures the elevation above the horizon the moon's located. And so it's just a straw adhered to a protractor, and you've got this string that dangles from the protractor with something heavy on the bottom to provide it with its weight. And so you just change the angle of the protractor by looking through the opening and lining up the moon. Like, remember, you need a reference point when you're doing your observation. So I would put like the lip of the straw, like the top edge of the straw's lip aligned with the top edge of the moon. So that way I'm measuring from the same point at all times. And then my protractor is going to show the angle that I'm holding this with respect to the horizon, right? If I'm holding it flat, I'm going to be at 0 degrees. Of course, it's going to be marked 90, even though it means 0 degrees above the horizon. So I'm going to have to subtract, measurements from this reading in order to get the accurate measurement. And so if this is 0, I'm going to have to return this as 10 degrees above. This is 20 degrees above, and kind of see that in a different way. Of course, you could always make your own number system over top of this if you want, but it's really good because it does give you an angle. And so that's what the elevation is going to be. And so students could do that in real life, or they can do it through Stellarium, which I'm going to show you in a bit. And so let's take a look at this clinometer, how you can make one. The next page on accident. So they use an eraser, binder clip, heavy enough object to draw time on around. If I try to use an eraser, I feel like it'll fall out of place.
This is the moment, tonight is the night. We'll fight till it's over, so we put our hands up like the ceiling can't hold us. Like the ceiling can't hold us. Can we go back? This is the moment, tonight is the night. We'll fight till it's over, so we put our hands up like the ceiling can't hold us. Like the ceiling
So in the video, you saw that you're going to need a partner to help you take a measurement with this instrument, because if you're holding it in the right place, you're not going to be able to turn your head around without moving the protractor to get a measurement. And so you could have a student or someone take a photo at the time that you've got it aligned so you can come back and get a good measurement. Remember, this is an opportunity also for you to work on the certainty of your measurements. Report your measurement according to the certainty that this instrument allows. There also, remember, in a structured inquiry activity, the teacher is responsible for coming up with the method. And there are a lot of different ways that you can develop a moon journal process, particularly with the date and times of observations. You can make it so that students are observing the moon when it's in the same part of the sky, which is going to be difficult because kids are going to be getting up at different hours of the day. And so for young kids, that's not going to be particularly favorable, but you could also have them just do it at one particular day. And then when that happens, though, you're going to run into a situation where the moon's not visible. And so you could shorten your moon journal down just to be a certain like time where the moon's going to be visible at the time you want your kids outside to observe. So it could just be like a week-long moon journal. But there are a lot of possibilities there. And so as the teacher, developing the structured inquiry activity, you got to think about what you want your students to be doing. Okay, so before we move into Stellarium, let's take a look at this protractor situation a little bit in more detail so that we can get it marked correctly. Remember that 90 degrees is going to be whenever this is laying flat. So technically that's when the moon would be at 0 degrees. And so as we raise it up, this is going to change to 10. It's going to change to 20. And so really what you can do is use the side of the protractor where the numbers are marked, and you could use that to help you guide your reference point. Or you can use this other side where it says 80 or 70, and you're just going to continue to subtract 90 from it, right? And so you'd get a negative number if you use it this way. So you could also make sure that you flip the protractor around, unlike the way they've adhered it, so that way when you lift it up, it's 100 on this side and 110 on this side, and then all you need to do is subtract 90 from each of these numbers to get your positive angle that you were getting. Okay, so Stellarium. I've actually created a whole folder of resources where students can go onto Stellarium and engage in inquiry-like activities. And so these are the 5 different units I've come up with. There's one on the amount of daylight, there's one on change in tilt, there's one on moon's orbit, there's one on scale properties and eclipses, and one on star brightness. And so this first one, we're actually going to just start with lesson 3, moon's orbit, since we're already talking about it. And so I'm going to go to stellarium.org to show you how you can download this for free on your computer. It's super easy. So once you type in stellarium.org, across the top are your different options for downloading it onto your computer. And this is free and free to use. It's encouraged that you use it for educational purposes. So if you have a Linux operating system, you would want to download that one. If you're using an Apple device, you want to download that one. I'm using the Windows 64-bit on my current computer. And then there's also a web version where you don't actually have to download it at all. But I believe there are probably some features that are not available in the web version that are probably available in the full download version. There's also a beta version and then a user guide. So after you download it, a little pop-up window is going to appear down here, and you're going to want to click it and tell it to install or finish downloading, and then install it on your computer. And then once the wizard is finished installing, you'll get this really cool desktop icon. So let's bring that up. And I do have a whole different set of trainings that I do outside of this class to teach people how to use Stellarium. And so I'm not going to go into the details of that in this webinar or in this web class, but if you're interested in one of those trainings, let me know and we'll set one up for you. And so What I'm going to do is I'm going to click this button to change it down to, not being full screen. And it opens up on the current time. And so it's really late right now when I'm recording this. So the stars are out. And this is exactly what it looks like right now because I've programmed Stellarium to open up on my particular location. So what I'm doing, the reason why I'm doing this is I'm dividing my screen into halves so that I can bring up the activity, which I have linked here. So when you go to the PowerPoint and click Stellarium Resources, you can have access to the folder where the activities are. And so I want to go to Moon's orbit, and I'm going to bring up the procedure. So this is the procedure that I've created for kids to follow along and do. So directions, open Stellarium, check. Number 2, locate the left sidebar by moving your cursor over the left side of the screen. And so I might have to, okay, there it is. So I might have to continue opening and closing windows and moving this around for me to manipulate everything in Stellarium. So just bear with me as I go through this. And so we're going to change your location to your location. We already checked that was correct for us. So B, close the window by clicking X in the top right of the window. Already done that. Number 3, on the left sidebar, locate date and time. Here it is. Click this to open the date and time window. It says leave this window open, and it's kind of over here on the side. It says leave this window open the entire activity. It's helpful to move it to the bottom right of the screen by clicking and dragging. So ask your instructor for help if you're having problems with this. And so it says use the provided date and times from the moon journal below to record observations of ecliptic latitude. And so click on the moon, use the scrolling wheel on your mouse to zoom in order to observe the moon phase. Draw it in the moon journal by shading in the circle where the moon is not illuminated, and also identify what time of day it is. Is it day, night, morning, or evening? Okay, so we're going to adjust the time to March 21st. And really, these dates can be anything you want in times. But this is just the date and time it was whenever I was making the assignment. Okay, so there I've set the date and time. Wow, it's daytime. So I would type in, or I'm probably going to have this printed out since I'm going to have to draw pictures on this. I'm going to type in that it was daytime. And so where's the moon? I've got to look around and find it. There's the sun. Oh, there's the moon. So the moon's out in the daytime, huh? Okay, and so it said to click on it and then zoom in. So I've got to use my scrolling powers here. I'm going to double click on it. We'll fix on it. Wow, okay, so that's what the moon's going to look like from Earth on this day at this time. And so it's a crescent phase. So I'm going to draw that in here, daytime, and then the ecliptic latitude. Where am I going to get that at? So I'm clicking on the moon. Here's ecliptic longitude / latitude. And so, but that's in the year 2000. So we want the one on the current date. So it's -4 degrees, 50 minutes of arc, and 25.3 seconds of arc. So we're not going to worry, even though a good measurement is provided to us for the purpose of this activity. We don't need these fine minutes and arc seconds. And so we're just going to report -4 degrees, even though it's close to 50. And I told you that's bad to do with measurements, but for this activity, it's probably preferable to keep things simple. And so I'm going to put in -4 degrees. Okay, so I'm going to scroll back out just a little bit, so that way I don't lose track of the moon when I change the date. So I'm going to change it to 3:22. And then the time is still about the same, but I'll change it anyways. Okay, there we go. And I'm going to move this out of the way. Double click on the moon so that it centers, and I'm going to zoom in. So pretty similar to the day before. It might be just a little bit smaller. Our ecliptic latitude now, though, is -5 degrees. -5 degrees, and it's still daytime. So I'm just going to continue this process. I'm going to change the date to the 23rd. The time still wants me to do this at 12. I've lost the moon, so that's why I got to zoom back out. There it is. Wow, it's getting closer to the sun now. That might be a note I could add on the side if I want it. Seems it's getting closer to the sun. And so, of course, this is not something your kids are going to be able to do safely other than using Stellarium. So I'm really liking this Stellarium activity that I've created. Wow, that little silver sliver is very thin now. Okay, and as I keep moving, you can probably make the prediction that it's going to disappear. So I've lost my date and time window. Oh, I still have it hidden. There we go. Pull that out. Bring this back to viewing window that I had. Okay, so we're going to change it to 3:24. Still 12 o'clock. And because I didn't zoom out, I've lost the moon again. There, oh, zoomed out way too much that time. Okay, so there's the sun, and I'm sure we just saw the moon over here. Oh, okay, now it's over here. Right, I must have skipped a day, or maybe I had the wrong hour. Yeah, it's not. It's still the correct hour. It's just not the correct hour to see the moon exactly right here. And so you could see that even at the same day or the same time on the next day, the moon moves quite a bit through its orbit. And so now we've got a point to where I can just barely see a silver sliver on this side. And this I'm going to zoom back out so I don't lose the moon. And then I'm going to change the date to the 25th. It still wants me to record this at noon. Okay, centered on the moon. Let's zoom in. And so we can watch this get larger and record that information. Oh, I haven't been looking at the ecliptic latitudes. Whoops. And so it's -5 now. It's actually been -5. It hasn't changed much yet. So we're kind of lucky. Okay, so 3:26. Zoom in. Now we're seeing that illumination growing. So our moon is now waxing. And so you can go through this. I'm going to jump ahead in our moon phase. We're going to go to 3:27. Oh, that's actually the next day. Okay, so now we're going to be at 15 hours, which is going to be like 13 is 1 o'clock, 14 is 2 o'clock. So this is going to be 3 o'clock local time. So it's still daytime. Lost the moon again. Got to zoom back out. Ooh, too far. Okay, there's the moon. I'll double click on it, zoom back in. Okay, so we can make the observation it's moving further away from the sun and it's getting more illuminated. In fact, I can see Mare Imbrium here appearing. And our latitude is back down to -4. So it didn't get any higher than -5, or any lower, I should say, than -5. And it's starting to get higher again. And I'm going to jump way ahead this time. We're going to go to the 18 o'clock, or the one at 1800. When you click that button, it goes to current day and time. And I have lost my window because I have messed this up by putting my window in the wrong spot. I've got to go back now. Oh, I still lost it, didn't I? I'm going to have to do this again. I need to bring it over here. Okay, so we want to change it to April 2nd at 1800, which is like 6 o'clock local time. Okay, don't Don't lose this time. All right, so I got to zoom out and find the moon. Wow. All right, so Stellarium can be tricky sometimes, especially while you're trying to use Zoom to do things. I think I've frozen it up. Let me just close it out and open it back up. Okay, so 6 local time on this day, the sun's starting to go down. So we could call this evening. And let's see, there's the moon. And so if we zoom in on the moon now, we get to see this moon phase. So this is a really good quality picture in Stellarium. You can even see the Copernicus crater there really well. And you can actually see how these craters are more visible along this line where it transitions from illuminated side to dark side. And so this line is actually called the terminator, and that's the best place to look at craters because you get the shadows cast on them by the sun's light hitting one edge of the crater rim, and it helps illuminate where it's at. Whereas you can see over here, some of those features now are becoming less visible because they're not getting the shadow effect happening anymore. And so these craters down here are very visible because of it. And so yeah, you get the point, right? You get to travel through the moon's orbit using Stellarium. Super fun and cool thing, and simple. So in your classroom, you might even lead that yourself and have the kids just copy it in and do the confirmation lab right there in the classroom. They would have a copy of the sheet and they could make their observations while you move through the particular times. And so at the end, I have some questions. Use your data to make a graph of the moon's orbit around the Earth. Okay, and then it says use a graph to answer the following questions. Let's get back to the presentation because this is what you're going to get if you do a full lunar month. You'll get a graph that looks somewhat like this. It may not start at -4, depending on the day you pick. It could start anywhere between +5 and -5. And so we can see that the moon oscillates or goes back and forth from 5 to -5, and it crosses through 0 every time that it makes this change. And so what type of activity is this? Well, if I'm asking the students to make an explanation on why this event happens, it's definitely a structured inquiry lab, right? And so they might come up with that conclusion that, well, the moon's orbit causes it to appear this way. So they may come up with this model on their own. You may have to assist them and get them thinking in terms of this, but the moon does have a 5-degree tilt to its orbit as it revolves around the Earth. And so it comes up above the ecliptic plane and it goes down below 5 degrees beneath the ecliptic plane, where 0 degrees is the ecliptic plane. That's where the sun is going to be positioned. And that 0 degrees is programmed into Stellarium based upon where the ecliptic plane is positioned. That's why I put on the data table ecliptic latitude rather than our elevation, which is what you might get if you're outside measuring a clinometer, right? So if you're trying to get this information with students with your clinometers, they're going to get different readings. They're not going to get -5 and 5. Instead, they're going to get things like 45 degrees, and then it's going to go up to 55 degrees. It's going to work its way back down to 40-some degrees throughout the month due to your position on Earth and how you're observing it. Okay, so if students are constructing the explanation, it's structured inquiry. If you're using this to confirm the moon's orbit being in a 5-degree tilt, that's a confirmation inquiry activity. And so then the activity moves into talking about solar eclipses and lunar eclipses, right? And so whenever the moon is on the ecliptic plane or at 0 degrees ecliptic latitude, it's directly in line with the sun and the earth. So that way, when the earth casts its light on the moon, the shadow on the side that's not illuminated is then projected onto the earth. And if you're standing within that shadow, you're going to experience a solar eclipse. Whereas with the lunar eclipse, the earth is casting its shadow on the moon, and so when the moon is within the shadow, it gets darker, and we call that a lunar eclipse. And so some of these questions just ask students to start interpreting the information on the data table. And so how many days does it take for the moon to make one complete lunar month? So they'll see through their observations that it goes through the lunar phases in about 27 to 29 days. And so it actually would be closer to 29 days. We call that a lunar month, whereas it actually only takes 27 days for the moon to make one full revolution. But because the Earth is in revolution around the sun, all the moon phases are not seen until the moon moves those extra 2 days around in the orbit to make up for it. And so what is the highest degree that the moon's orbit achieved during its orbit? Well, we saw positive 5 degrees, and if we would have done it throughout, we would have seen a negative 5 degrees for the lowest degree of its orbit. And so question 4 then asks, why is it unlikely for a solar eclipse to occur every month? And so we see that image here on what eclipses are, and we've just talked about our theory about why we think the moon's angle changes. And so what conditions must be true for a solar eclipse to occur? Well, they have to be lined up. And so if the moon is above 5 degrees or anywhere below the ecliptic plane, the shadows here are going to be below or above the Earth or below or above the moon. So we're not going to see an eclipse. So remember, that tilt is the reason why we don't see one every month when the moon is in full moon or new moon phase. Okay, so that was the moon's orbit. Now let's talk about this other activity, scale properties / eclipses. And this one's just really cool. And so here are the directions. And so it says to open Stellarium, change the location, and then it says to open the date and time window, and then you're going to change the date and time for the next American total solar eclipse, which is going to take place on April 8th, 2024. Change the date to 2024-4/8 and to the time at 10 o'clock in the morning. Click and drag the horizon so that you're facing the southeast side. Move up until you see both the sun and the moon on the screen. Click on the sun. Okay, and so we'll get started on Stellarium. We'll start doing some of that, and then April 8th, 2024, the time at 10 o'clock in the morning, and I'm apparently looking at the ground. So I need to zoom out here and get myself oriented. Okay, so there's the sun. Oh, and the moon, we can already see it starting to begin the eclipse. It's right there. So I'm going to zoom in. Oh, it's not quite there though. You can see the moon is over here. And so let's pause and come back to the assignment. So I want to come back in the folder to this assignment. I want to bring up this set of directions. Okay, so we made it down here. Find the sun and click it. Record the diameter of the sun and the distance from Earth. And so the units are provided in kilometers and astronomical units. And then we're going to record the magnitude of the object. This is called the visual brightness by most people. So bringing back up Stellarium, click on the sun. So the information that we wanted again was the diameter. So let's see here. There's the distance. So it's 1 astronomical unit. So that's question number 2. Here's the diameter. Wow. 1392000.0 kilometers, or that would be 1,392,000 kilometers across. Okay, and so we would record that information. Oh, and its magnitude is -26. Negative is really bright, right, in terms of star brightness. Whenever the more negative it is, the brighter it is. So it appears to be a really bright object in the sky. All right, here's the moon. Let's go back to our lab activity. Use the fast forward or rewind to change the time and locate all the remaining objects in the sky. Oh, I brought up the wrong assignment. I was wondering why I was asking about brightness. I want the extension activity. I apologize. So we still got the sun's diameter, we got the sun's distance, and then we want the apparent diameter. So that's how many degrees in minutes. How big does it appear? Not how big it truly is, how big does it appear? And so apparent diameter, true diameter, remember, was 1,392,000 kilometers, but it only appears to be 0 degrees and 31 minutes of arc wide. Only 31 arc minutes wide is the diameter. And so that's a trigonometry measurement that we use in astronomy a lot. We talk about angles. Okay, now we want to do the same thing for the moon. We want its diameter, distance to Earth, and its apparent diameter. Okay, one moon is right there. Diameter, wow, only 3,474 kilometers wide, but its apparent diameter is, wow, just about the same as the sun, 33 arc minutes, whereas the sun's only 31 arc minutes. So they almost have the same diameter in appearance, and that's because the moon is actually closer to us than the sun. So if we find the distance, here it is, it's 0.002373 astronomical units, whereas the sun was one whole astronomical unit away. This is only 2,000ths of an astronomical unit. So the close distance of the sun of the moon makes it appear bigger than it is. And the further distance that the sun is away from us, the shorter it appears, or the smaller that it appears. So this is kind of like a ratio thing, right, that we're getting involved in. A little bit of math here. All right, so let's watch the eclipse take place. So we can fast forward time a little bit. So it's because of their apparent diameters being so close to one another, appearing to be almost the same size, that an eclipse is visible. So that's what it's going to look like in West Virginia whenever the next eclipse happens. So kind of neat. And so my question is, do you guys think that that is a confirmation activity, or do you think that that's a structured inquiry activity? So confirmation inquiry or structured inquiry? So think about that one, and we'll discuss it at the teleconference. All right, so let's move on to another activity. This is about the sun, and so this is the amount of daylight. And so this one, you have a data table where you're basically tracking the time and the altitude of the sun. And so I'm not going to go into Stellarium and show this one to you in the interest of time, but basically just like watching the moon's orbit, we're going to watch the sun's transgression across the sky those days. And so on 4 particular days, each of the equinoxes and each of the solstices will do this. And so what students will visually see in Stellarium is in the winter, the sun doesn't come up as high, and it's only out for this many hours, right? So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hours. And so during the equinoxes, both in the fall and the spring, it comes up to about 50 degrees above, and then it goes back down, and it's only out for this number of hours a day. And where in the summertime, it comes up and gets even higher in the sky, and it's out for a longer period of time, many more hours. And so then you come from that and can turn this into a structured inquiry activity by asking, well, why does this happen? So can you explain why we see this happening? So students can also do this activity that I have called change and tilt, where it programs or directs students to looking at just one side of the sky and just the first 3 hours of sunrise on those 4 days. And so they'd see during the equinoxes, the sun comes up here in the middle. And so they're going to plot the point at these hours where the sun is. And so on the next day, or over here on the next date, It's going to be summertime, so it's going to be up here at positive 23.5 degrees in the celestial sphere. And so in that first hour, it'll be here. The next hour, it'll be up here. And the next hour, it'll be up here. And then in the winter months, it's going to be down here, and down here. And so, again, it's another observation of the same phenomenon. Why does the sun come up lower in the sky in the winter, but higher in the sky in the summer? Why does this thing happen? And so students can work towards making this explanation about the Earth's tilt, and it orbits around the sun. And so because the Earth continues to tilt in the same direction, regardless of what time of year it is, causes the angle at which the sun appears to be in the sky to change above the Earth. So in the summertime, whenever we're pointing towards the sun, it's going to go up higher in the sky. It's going to get closer to our location, being over our heads, not quite over our heads, but it's going to be on our side of the northern hemisphere. So it's going to be out for a longer period of time, whereas in the winter, it's going to be over the southern hemisphere. So it's going to be closer to the southern part of the sky, lower in our sky, and only above the horizon for a short period of time. And so, again, is this confirmation or structured? It just depends on the order in which you present the information. And so how could you make this confirmation? And how could you make this a structured lab and still teach the same scientific content in both? So think about those, and we'll discuss that at our teleconference. All right, celestial sphere. Now we're going to talk about the stars before we wrap this thing up. So I mentioned the celestial sphere on the last slide. What is the celestial sphere? Well, the celestial sphere is actually an idea that was created by Greeks who were studying astronomy for the first time, and they actually saw all of the stars fixed in a position in the sky. And so they thought that these stars, and by the way, you can get a celestial sphere like this at my science shop. If you click this link, you can buy one there. But the Greeks thought that for the stars to be able to stay in only one position, they had to be attached to something. They couldn't just be floating around. And so they thought that the stars were all fixed in a position in this sphere that wrapped around the universe. And so it was due to this rotation of the sphere that made it look like the stars changed positions in the sky throughout the night and throughout the year. And so they always viewed the Earth in the center of the universe. And so they thought that these planets and the sun and the moon had their own spheres that they were attached to, and that they could move any direction that they wanted within those spheres, because these were named after the Greek gods, right? We saw these figures in their mythology or in their history as being their gods, and so they were free to roam the heavens any way that they wanted, is what they viewed. And so that's why these things were seen wandering around the sky. In fact, the name planet, if you translate it back through the Latin language, actually interprets wanderers. So they're literally named the wanderers of the sky because they weren't fixed in position like the stars were in the celestial sphere. And so just like the nature of science attribute, we talked about science being tentative but durable, and so more evidence will change particular theories. Here's another example of that. And so Copernicus actually came up with the idea of a heliocentric universe where the sun was in the center and the planets, including the Earth, would orbit around the sun, and that the moon was in orbit around the Earth within its orbit. And so this was not actually really popular, and that was mainly because there was not a lot of scientific evidence to support this claim at first. And so it was really convincing people with evidence that made it become the accepted theory. And so very quickly, though, about celestial coordinates, it's more like a grid system. Like we have latitude and longitude for planet Earth. This is like the latitude and longitude of the heavens and the stars in the sky. And so this line here is the ecliptic plane, and this red, or actually it's orange, line wraps around the sphere. It's not pictured on the back half, but this is where the Earth's equator lines up with the celestial sphere, and so we call this the celestial equator, and that's known as 0 degrees declination. Not to be confused with the 0 degrees ecliptic latitude from our activity that we went through. That's what the ecliptic plane is. And so notice that the ecliptic plane is not lined up on 0 degrees declination. And that's because we see the sun moving up above the ecliptic plane in the summer and down below the ecliptic plane in the winter. And that's due to Earth's tilt as it revolves around the sun. And so we use declination as the degrees above and below the ecliptic plane, and we use the term right ascension to describe the position east or west or left or right of the 0 hour mark. And so at 0 hours and 0 degrees, this reference point is kind of like the origin system of the celestial coordinate system. This is like 0.00 in the sky. And this is also where the sun is positioned on the vernal equinox, right? So it's kind of like marking the beginning of this cycle as well. And so anything that's an hour off of this is going to take an hour to move into the position where the thing was before. And so that's why we mark them in hours, because it's based upon the Earth's rotation and how that line or that meridian lines up with the Earth, wherever you're standing. Okay, and so the Earth's big points here. The Earth's rotation causes everything in the sky to appear like it's moving continuously from east to west. And so that's a change to the Greek theory of the universe, right? They thought this sphere was rotating and causing that appearance, but it's actually the Earth's rotation. And that star positions do not appear to change their position in the celestial sphere over short periods of time due to how far away they are from the Earth. They actually do move in reference to the celestial sphere. It just takes a long time for it to become evident. And the sun, moon, and planets are closer to the Earth and have a larger apparent change in position. And so remember, these things are termed the wanderers, or what we could call planets, other than the sun and moon are technically not planets. So maybe wanderers is actually a better term to use anyways. And so you can actually turn on the grid system, the right ascension and declination on Stellarium. And I still have it brought up, so I'll show you how to do that. So if you just click down here on the bottom window, the grid system, it will appear. And so you can see the hours. This is 1 hour, 25 minutes right ascension. This is positive 10 degrees declination. And so we can actually locate where the moon is according to the celestial coordinate system. When we click on it, we can go up here to RA/dec. So it's at 1 hour, 15 minutes right ascension and positive 8 degrees declination at this current time. And what about the evidence that actually changed the Greek view of the stars in the heavens? So Galileo created the first telescope during the Renaissance period, and he collected a lot of information using that telescope for the very first time. One of the things that he did was he observed Venus moving in the sky. And so you'll notice that Venus has phases similar to the moon, but they're not in the same sequence in which the moon phases occur. And so this led Galileo to provide evidence that that Venus actually has to orbit the sun rather than the Earth. And also retrograde motion of Mars was used to demonstrate the succession of planetary orbits. So it was first Mercury, then Venus, Earth, and Mars would be after it. And so that retrograde motion helps to explain that. And so I'm going to demonstrate these two things on Stellarium, and then we will be finished with class. And so I know this class is a little bit longer than the other ones. Some of them have been a little bit short, so that'll make up for it. But let's zoom out here. And I just saw Venus here. So if I zoom in to Venus, and remember the sun is up above here. So if I zoom in, so like I'm using my telescope like Galileo, I'm going to see Venus like this, fully illuminated, almost like in a full moon phase. So if I zoom back out, and I'm going to change the day, just like we did with the moon journal, but for Venus instead, if I just change this daily, notice how the position of Venus changes. Whoops. It's seen right now getting closer to the sun. And if I were to zoom in now, what would Venus look like? Still looks rather full. So we're going to have to progress some more. So when does it no longer appear full to us? Well, it actually is whenever it essentially eclipses the sun, or what we call getting in conjunction. Okay, and so it's going to be full. And in fact, we wouldn't be able to see Venus because it's too bright. You wouldn't be able to use a telescope to safely look at Venus like this. But watch what happens when we get on the other side of Venus. After it passes behind the sun, let's take a look at the current Venus phase. So still full, but you'll notice that this side is starting to get dimmer. So if it's a full Venus phase, that means that it can't be between the Earth and Sun, because the light has to be reflecting off of it. So it's kind of at an angle to the side. Let's see here. Keep our eye on Venus while I move through the days. All right, let's take a look now. So we can see this starting to turn into like the moon's gibbous phase. And so this indicates that this side is pointing towards the sun. And so as we continue to do this, it's going to get thinner and thinner and thinner. And so this order in which the moon phases take place is different. Right, when the moon is on this side of the sun, it actually is getting brighter, becoming fuller, whereas when Venus is on this side of the sun, it's getting darker, and to the point to where when it lines up and actually has an eclipse with the sun, we call that a transit on this side. You could actually watch Venus pass through the sun. It's something called the transit of Venus. And so I'm not going to show you a video on that in this session, but you really should check that out and learn about the transit of Venus. This is a really cool phenomenon. All right, let me see if I can find Mars really quickly. I might not be able to, but I have to fast forward time here until it appears. Looking for Mars. We're looking, well, there's Saturn. So here's the ecliptic plane. It's going to be somewhere on this ecliptic plane. I don't think that's it. Nope, that's a star in Terry's. All right, so let's watch and see if Mars will rise over here after Saturn. There's Jupiter. There's Uranus. Of course, I'm up in 2024, so I don't really know where Mars is in 2024. There we go. There it is. It just appeared. So when we take a look at Mars, you can actually watch Mars go through its phases as well, but it's going to also change its position in the sky. So watch how Mars moves in the sky whenever I change the date. So it's moving one direction. Well, the moon just passed by. Now watch as it starts to curve, it's going to start heading back in the other direction. This is what's meant by retrograde motion. And so when a planet does that, it actually means that its orbit is beyond the Earth. Okay, so just wanted to show you guys a couple examples of inquiry and teach you also just a little bit about planets and their orbits as well. So I hope you guys enjoyed this. And if you have any questions about any of the content, make sure that you email me at jrebels@fairmontstate.edu.